Hello and welcome to the STEM Tutor. In this lesson, I'll be discussing osmosis, isotonic, hypotonic, and hypertonic solutions, along with a few examples. Let's begin the lesson. Students struggle with tonicity when taking chemistry and biology classes. It can be confusing distinguishing between percents, cell and solution environments, hyper or hypotonic solutions, numbers, and a bunch of terms that almost look like they mean the same thing, especially in a test or during a lab. You might find yourself getting lost in the material. My goal is to help you master tonicity and thus conquer the world. Well, almost. To start off, let's talk about what osmosis is. Water is our solvent, and whatever is in the water, like sodium chloride or glucose, is our solute. Water will travel in either direction across the semi-permeable membrane, which is a phospholipid bilayer that does not allow solute to leave. Water will travel from an area with low solute concentration to an area with high solute concentration. Let's see this in action with different solutions. Isotonic solutions involve two environments: the environment that is inside the cell and the environment that is outside the cell. The left side is our cell. The dissolved solute concentration is the same in both environments. Before we move on, answer this question. The movement of water passing between both environments to equalize the solute concentration is steady and even. What is the term for this? Equilibrium. Let's see this in action. As you can see from my animation, the solute concentration and amount of water inside the cell is pretty much the same concentration as the solution it's in. So water molecules aren't going to pass in and out as much, if at all. Moving on, hypotonic solutions are not at equilibrium. In fact, it is the cell that has the higher solute concentration than the solution it's in. Over time, water molecules will pass back and forth across the semi-permeable membrane, but most of the water is coming from the outside. The cell is trying to achieve an internal equilibrium with the solution it's in, and the solute particles block some of the cell's water molecules from leaving. What do you think will happen to the cell? The water will expand with every molecule that enters through the semi-permeable membrane, possibly causing it to burst. Now let's talk about hypertonic solutions. Hypertonic solutions are the opposite of hypotonic solutions. The left side again is our cell. As you can see, it's rather dilute. The concentration of solute or sodium chloride is greater outside the cell. Remember how in a hypertonic solution the solute particles can act as a barrier for water to leave the cell? Well, we are seeing the opposite. Water molecules are leaving the cell more freely because they are not as obstructed by the solute particles. Water isn't entering the cell because the molecules are being blocked by the higher concentration of sodium chloride. What do you think happens to the cell in a high salt concentration if water is slowly leaving the cell? The cell will shrivel up, kind of like jerky. Let's talk about numbers and examples. A 0.9% sodium chloride solution is isotonic to animal cells. This is the standard literature value, which means it doesn't change. It's 0.9% 24/7, not 1% on Wednesdays and 15% on Sundays. Knowing this, let's do some examples. Your cell contains 0.9% sodium chloride. However, the outer solution also has a solute concentration of 0.9% sodium chloride. If you remember, when both numbers are equal, there isn't much of a change. This is an isotonic solution. Here's another example. We know that 0.9% is greater than 0.3%, just as much as we know that 4 is greater than 2, right? The cell, this time, contains the high solute concentration. The environment is therefore hypotonic, meaning there is a lower solute concentration outside the cell. Water will rush into the cell because it's going from a low to high concentration, causing the cell to possibly burst. Here's another example. 0.2% is the inner concentration, so that's what's in the cell. And 0.8% is the outer concentration, the solution. We know that 0.8% is a larger number, and thus a higher solute concentration. Remember, water moves from low to high, so this solution is hypertonic. Water will leave the cell, causing it to slowly shrink. Now let's do a comparison between these three samples. The cell concentration is 0.9% with these concentration values. Pause the video and work this out before continuing. And here's how the problem is worked out. Beaker 1 is hypotonic. Beaker 2 is isotonic. And beaker 3 is hypertonic. And you can mess around with these numbers. And that concludes this lesson.